Hi, welcome back to my channel, Physics from 5 KSSM. Today we start Chapter 5, Electronics on topic 5.1, Electrons. In this video, I will discuss three learning standards. The first one, describe thermionic emission and cathode rays. The second one, describe effect of electric and magnetic fields on cathode rays. The third one, determine velocity of an electron in cathode ray tube. First of all, let's discuss what is the meaning of thermionic emissions. Okay, watch this video to understand the concept of thermionic emissions. Thermionic emission is the process of electron released out from the surface of heated metal. Under the surface of metal, there are a lot of free electrons with a certain amount of kinetic energy. When the metal is heated up, electron will gain enough energy and able to free itself and release from the surface of metal. This process that show some electron escape from the surface of heated metal, we call it thermionic emissions. The rate of electrons released out through this process depends on three factors. The first one is temperature. The higher the temperature, the higher the kinetic energy supplied, thus more electrons will be released out. Or we can say rate of thermionic emission increases. The second one is surface area of the metal that heated up. So the amount of electrons that receive enough energy to escape from the surface of metal also increases when larger surface area of metal is heated up. The third one is type of material, also related to specific heat capacity of material. The smaller the specific heat capacity of metal, the metal will be heated up faster, thus more number of electrons will escape from the surface of metal per second, or rate of thermionic emission increases. The electrons that release through the process of thermionic emission, it will stay at the surface of metal. Can the electron move through a vacuum without a conductor? Can that electron that released through the thermionic emission then travel in vacuum? Let's watch this video, the second video, to show how electrons able to travel in vacuum. So this is vacuum tube. Vacuum tube consists of the filament, anode and cathode. Anode and cathode is connected to EHT power supply. Filament is connected to small voltage 6 volt. The filament glow and heats up cathode to produce electrons through thermionic emission, electrons, and then accelerated towards anode and pass through a cylinder anode to produce a beam of electron that travel at high speed. So this beam of electrons that travel at high speed, we call it cathode rays. Inside the tube here are vacuum. So cathode rays can travel in vacuum without conductor. Let's try to answer some questions under this activity. You can refer to activity 5.1 in your textbook. What is thermionic emission? It's the process of electrons released from the surface of heated metal. What is a function of 6 volt power supply, which is connected to filament? an EHT power supply. As you can see before, the 6-volt power supply to heats up the filament for thermionic emission. The EHT power supply is to produce high speed of cathode rays. Means it supply high voltage across anode and cathode, okay, that able to accelerate the cathode rays. Why must the tube be in a state of vacuum? Can you imagine if here is not vacuum, there are a lot of air particles. So when cathode ray travel, it will collide with air particle and causes energy loss. When the energy loss, the electrons that hit the screen with low energy thus produce a dimmer light. So cathode ray travel without energy loss. How can cathode rays be produced in vacuum tube? As you can see, electron accelerated from cathode to anode when receive high electric potential energy, then pass through the focusing anode to form a beam of electrons that travel at high speed. Let's explain thermionic emission and production of cathode rays in vacuum tube using extra high tension power supply. Okay, let's look at this one. The 6-volt power supply is to heat up filament. The filament, when glow, it will heat up cathode. The cathode will release electrons through thermionic emissions. Electron beam is produced, accelerated towards anode. Through the focusing anode, it will continue to travel in vacuum. EHT power supply, high voltage supply high kinetic energy to cathode rays to supply voltage across cathode and anode and supply electrical potential energy to electrons. Thus, electrons able to travel at high speed. Okay, next we want to discuss the properties of cathode rays. Just now we have shown that the definition for cathode rays. Cathode rays are beams of electrons moving at high speed in a vacuum. So in this part, we want to discuss does cathode rays will be affected by electric field or magnetic field or not. So in this activity, we are going to use deflection tube and multi-cross tube. Activity 5.2. This one is to study effects of electric field on cathode rays using deflection tube. Apparatus, deflection tube, 6-volt power supply, EHT power supply, and connecting wires. So you can see from this diagram, this is deflection tube, deflection plate. One plate connect to the positive terminal, the bottom plate connect to negative terminal. Means when S3 is on, there will be potential difference across the two plates or electric field, okay, between the two plates. What happens when S1 and S2 is on? When S2 and S1 is on, these circuits are completed. Filament will glow, heats up cathode, electron release out through thermionic emission, and then the electron will be accelerated to anode. It will produce beam of electrons that travel and hit the screen. Cathode rays travel in a straight line because this one is vacuum. What happens when S3 is on? The above plate is positively charged. The bottom one is negative. S3 is on. So you can see the cathode ray deflected in parabolic path upwards towards positive plate. If we reverse the terminal of EHT, it will be deflected downward because downward become positively charged plate. Okay, you can watch this video to show how cathode ray is produced. Through thermionic emission, we have discussed before, Electrons accelerated towards anode due to EHT power supply high voltage across anode and cathode. There is a part, we call it grid control. This grid is connected to Y gain to control brightness of light produced on the screen. When the grid is connected to more negative potential, it will repel more number electrons or prevent electrons to go to anode. Less number of electrons pass through anode, it will produce less brightness of light form on the screen. So the grid actually control brightness. Okay, let's look at the situation. We can explain it again. S1 and S2 turn on. Okay, there's no deflection. The cathode ray travels straight line and hit the screen. When S1, S2, S3 turn on, for the first part, above part is positive, thus deflect upwards. If the bottom part is positive, it will be deflected downwards. Okay, let's try to answer some question here. Switches S1, S2 turn on, cathode ray accelerated in straight line. Switches S1, S2, S3 turn on, cathode ray deflected upwards towards positive plate in parabolic path. It always deflects towards positive. Switches S1, S2, S3 are turned on and the potential difference at deflection plates is reversed. Same as this case. So cathode ray deflected downwards towards positive plates in parabolic path. Okay, let's watch this video to show how the cathode ray affected by electric field. If no potential difference across above and below plates, the cathode ray will travel in a straight line. The plate is connected to Y gain, where we can input any voltage. Let's say we input voltage across above plate and below plate. For example, we input one battery here. This is positive and this is negative. So the above plate will become positively charged and bottom negative. So you can see the cathode ray deflected up. On the screen also, you can see the spot that produce also deflect upwards. If travel straight line without electric field, it will place at the center, the spot. Now reverse the terminal, the bottom will become positive, above negative, so cathode ray deflect downwards. So you can see the spot on the screen deflect downward. What happens if the voltage is removed means no more voltage across the two plates. Cathode ray travel in a straight line, so hit the screen at the center of the screen. No deflection. So what can you conclude from the video just now? We proved that cathode rays travel in a straight line in vacuum. The second one, cathode rays can be deflected by an electric field. They are deflected towards positive plates in parabolic path. and cathode rays are negatively charged because it always deflected towards positive plate. As we know earlier, we also know that cathode rays actually beam of electrons. Thus, it carry property of electrons. Okay, activity 5.3. Aim is to study effects of a magnetic field on cathode rays using Mortis cross tube, apparatus, Mortis cross tube, 6-volt power supply, EHT power supply, bar magnet, and connecting wires. So this is the diagram for the Mortis cross tube. For the deflection tube just now, we just replace it with Mortis cross here. Mortis cross also connected to EHT power supply. Okay, let's watch the video to show how the Mortis cross show the effect when cathode ray travel. Okay, so this is Mortis cross connect to high voltage power supply. Through thermionic emission, electrons released out will travel in a straight line. At first, before EHT is on, electron just stay at the surface of cathode. So initially, when the filament glow, you can see the image of the Mortis cross form at the center of the screen with yellowish color of light. So this shadow actually cast by light from filament. As light travel in a straight line, you can see the shadow form exactly at the center of the screen. Now, what happens if the EHT is on? Meaning there is a potential difference between cathode and anode. What happens? The shadow will become darker and you can see a green color produced surround the shadow. So the green color is caused by fluorescent effects. When cathode ray hit the screen, produce light or fluorescent effect. When you bring bar magnet towards the shadow, you can see the shadow cast by the cathode ray will be deflected and distorted. Okay? The shadow that formed by light from the filament still stay at the center. So you can see there are two shadows formed on the screen at this stage. The one that formed by the cathode ray will be deflected and distorted. The one that produced by light will stay at the center because light cannot be deflected by magnetic field. Okay, let's answer some questions. Number one, state your observation of the shadow form on the fluorescent screen when switch S1 is turned on. So a shadow or Mortis cross form on the screen because light travels in a straight line. So you can see a shadow with yellowish color light around the shadow. Switches S1 and S2 turn on. Shadow or Mortis cross become darker with green light around it. So this one is caused by fluorescent effect. Switches S1 and S2 are turned on and the north pole of magnet is brought to the side of Mortis cross tube. Okay. Two shadows are seen on the screen. The shadow cast by light, thus affected by magnet, does not affected by magnet, stays at the center. This one should be does not affected. The shadow cast by cathode ray will be distorted and deflected. Okay. Explain your observation when north pole of magnet brought to the right side of Mortis cross tube. Let's say this is the Mortis cross tube and this is the bar magnet. North pole is bring to the right side of the Mortis cross tube. How to determine direction of deflection of the shadow, you can apply Fleming's left-hand rule. Direction of the magnetic field always pointing to south, north to south. So your forefinger you must place into the screen. The current finger you must place opposite to direction of cathode rays. Cathode rays travel to the right, to the left, means you must place your current finger towards right. Okay, magnetic field is into the screen, current towards right, so your thumb pointing upwards, meaning the shadow will be deflected upwards. Okay, so this is how we use Fleming's left-hand rule to determine direction of deflection of Marquis cross shadow. Okay, let's explain more about this situation. The first situation, S1 turned on just now, you can see a shadow with yellowish color light. Okay, surround the shadow. So this one is caused by light that travel in straight line. S1 and S2 are turned on. You can see a shadow form with a green light surround it. So this is caused by fluorescent effect when cathode ray hits the screen. S1 and S2 turn on, and there's a magnet placed near the tube. Let's say this position, left side. Okay, so what happens to the shadow? You can apply Fleming's left-hand rule here. You place your forefinger towards the right, north to south. The cathode ray is moving out from the screen, meaning your current finger must place into the screen. Okay, your forefinger to the right, current finger into the screen, thus the thumb will point downwards. Thus the shadow will be deflected downward, as shown here. Okay, let's discuss more on potential difference across cathode and anode. Electrons will achieve certain velocity because receive electrical potential energy from EHT power supply. Electrical potential energy gained by electrons, we can discuss it from the formula that we discussed in chapter 2 electricity. Potential difference equals to electrical energy per unit charge. So from here we get E equals to QV. So in this case, to determine velocity of an electron, we just calculate for one electron. Thus Q equals to NE. N equals to 1 because one electron, so Q equals to E. Thus, electrical potential energy gained by one electron equals to E equals to charge of one electron times voltage of EHT power supply. So we get this formula E equals to EV. Charge of one electron is always given 1.6 times 10 to the power of negative 19 coulomb. So from this formula, we can see the relationship between electrical potential energy supplied to one electron is directly proportional to voltage of EHT power supply. The higher the voltage supplied between cathode and anode, the higher the electrical potential energy supplied to electrons. Thus, electron receive high kinetic energy, or we can say the speed or velocity of electrons also is higher. Okay, so you must be able to determine velocity of an electron in cathode ray. So let's discuss how to determine the velocity of the electrons. By applying principle of conservation of energy, as we know that cathode ray travels in vacuum tube without any collision, so we can assume no energy is lost. So all the electrical potential energy supplied to one electron is equals to maximum kinetic energy of an electron. Thus, EV equals to half mv max squared. Vmax is the maximum velocity achieved by electrons. So in this case, we just calculate velocity of one electron to represent the whole beam of cathode rays. Because we only have the information on charge of one electron and mass of one electron. Unless you know number of electrons in the cathode ray, then you can calculate for the whole cathode ray. But in this case, one electron is enough to represent the whole beam of electrons. Okay, let's look at example 1 here. Figure 5.5 shows electron beam accelerated from cathode to anode in a vacuum. Potential difference across cathode and anode is 550 volt. Mass of electrons is given. Charge of electrons, okay, also given. What is electrical potential energy of an electron? Okay, remember the formula just now? EV, yeah? So you just take charge of one electron, multiply voltage across anode and cathode. So we get 8.8 times 10 to the power negative 17 joule. What is kinetic energy of an electron when it reaches at the anode? Okay, kinetic energy gained by electrons equals to electrical potential energy of electrons. Okay, the same value as we apply the principle of conservation of energy. Then what is maximum velocity? So you can just use the formula half mv squared equals to EV. So you get V equals to square root of 2EV divided by m. The EV already calculated above here, 8.8 times 10 to the power negative 17. So you just substitute here, divide by mass of one electron. Thus we get 1.39 times 10 to the power 7 meter second to the power negative 1. Okay, that's all my video for today. I will continue in the next video to discuss formative practice 5.1. So you can just go and try first, then you can come back to check the answer. Okay, that's all. Thank you for watching. Bye.